Hey everyone, this is Mathmetrics, and welcome to episode 9 of GridSchool for Bitwig 3.0. Today I'm continuing my 4-episode series on logic and all the cool things you can do with logic in the grid. As with all of my videos, I'm assuming you've watched all of the earlier episodes because I explain new concepts and techniques one by one, and each new video builds upon concepts and techniques I've already explained in earlier issues. So if you haven't seen the earlier episodes in this series yet, I recommend you go find my playlist and start from the beginning and work your way up to where we're at now. You can find a link to this playlist in the description for this video. Also, in today's video, I'm going to be showing you some more advanced use for logic and messing around with gates and triggers, making very unusual gates and triggers with logic. But I'm still showing them to you in the context of the way gates and triggers are supposed to be used in the grid, right? But I pointed out in the last video that Polarity, who's a great sound designer and producer and also makes lots of good YouTube videos, Polarity did a great video on logic that shows using gate signals in a very non-traditional way, like not really using them to control gates, but instead to control sounds and do kind of crazy, cool, weird things with sounds. So I highly recommend, you go watch this video at some point and learn about other non-traditional ways you can use logic. I'm going to stick with the more traditional way. As I've pointed out in previous videos, lots of things in the grid are color-coded to sort of guide you towards their intended use. And all these yellow logic-looking things are meant to basically drive logic input ports on things like envelopes or oscillators or whatever. But you can connect up logic signals to other things entirely and get some really interesting effects. So that's what a lot of what Polarity's video goes into. So check that out. I'm probably not going to cover that in my series because I don't want to reinvent the wheel. Okay, so we left off at a basic discussion of what all the logic stuff's about. We're just going to keep going now with some more advanced use cases. So here's a sequencer. It's a data sequencer that's spitting out gates, okay? And I don't want to hear it right now, so I've hooked it up with a button with an AND gate, an AND test, if you will, so that we're only going to hear this if I also make the button on, which makes this AND comparator true. So here we go. Now we're hearing the gate, the gates rather, that are being generated from this sequence. And if I change the order, we've got different gates now, but I can just turn it off with a button. You're going to find yourself doing stuff like this all the time while you're building grid devices. Is you're going to want certain things to happen only when you want them to. And you can even go so far as to, down here on the main grid device, if I open up the shortcut tab, and let's go to a new page. Let's just make a brand new preset page for it and drop that in. Okay, so back here in the grid device, if I want to hook up a shortcut to the button, I can do that. And now I can use the remote controls tab to turn something inside the grid on or off. Okay, so that's a really useful technique. These buttons to control with some sort of logic comparator, whether it's Boolean comparators or math comparators, you can just have manual control over that. All right, so that's one cool trick for gates and stuff. But the main thing I want to show you is how to take these vanilla, simple, very uniform gates and make them different. You'll notice that these are eighth notes. So if I turn all of them on, and we turn it on, it's a very even, uniform, regular distribution that we see up here. The eighth note, each eighth note is on for half of its duration, so it's like basically on for a 16th, and then it's off for the other 16th note. And so that's why we hear effectively, if I were to draw out in a piano roll, 8 16th notes with a 16th note space in between each one. That's effectively what this gate device does by itself. okay? But you can't change that in the gate itself. If I click this gate and I look for something that lets me change how long those things are, right? In other synths or sequencers that have a sort of gates, a gate section or a steps section, they sometimes call them, you usually have a way to like drag these to the left, highlight a couple and drag them to the left to shorten up the gates on some of them and keep other gates longer. Can't really do that with this particular generator. Now it does have an interesting mode where if I do something like this, and I flip it into a gated mode by clicking this T, now what it's going to do is it's going to string these 3 eighth notes together in a legato kind of gate. And so it's going to hold down a single gate for the duration of those 3 and hold down another single gate for the duration of those 2. And you'll notice that since this gate here at the end wraps around into these 3, it just treats them as one long set of 4 eighth notes that it keeps the gate open for. So, triggered mode will always trigger each one like for half of its duration, a 16th note, it'll be triggered on, and then for the other half of its duration, it'll be triggered off. Okay, so let's go back to solid eighth notes again. And let's put something extra in here to change the length of these. This is where these specific logic devices come into play. The most useful one is gate length, which, oops, if I actually hook it up correctly. All right, so now we have a thing that's finally giving us some control over the length of these gated signals coming out of the sequencer. If I turn this way down to a very short millisecond value and we turn this on, you see we've got tiny little blips that are effectively like short little triggers. And in fact, they're so short that if you look at the envelope over here, they never stay on long enough for the attack to rise all the way to an audible volume. Instead, they're rising about this far and then shooting straight across and releasing because the gate's so short. Now, as I start increasing this value, we start hearing it because now the gates are just wide enough that they're having enough time to trigger all the way close to the top of the attack part of the envelope. And as I keep making the gate longer, and now I'm going way beyond the default behavior. Let's find where it's like almost keeping one open for each. There we go. Right about there at this project tempo. Because my release is slower, it sounds like one merge note, but if I slow the release down, right? So the bottom line is that if you want to control the length of some gated signal that's too regular for you, this is how you can control the length of it right here with a gate length device. Now, these other things are, well, the clocks are special. We'll talk about those in a minute. Gate repeat is a bit different. Let's see if I can show you a good use case for that. I'm going to unhook this. We're going to get rid of this logic test for a minute. Just disable it. So now if I turn the button on, we have a gate for as long as the button is on, just like me holding down a keyboard key. And so this envelope will flip up to the top and stay at the sustained value for as long as the button is on. And because this gate, this logic gate, this AND comparator is disabled, it's effectively not there. Okay. Let me just go ahead and get rid of it just so you're not confused. Hey, delete. Okay. So what a gate repeat does is it takes the signal coming into it and it says, basically keep repeating whatever gate comes into me every 50 milliseconds. Okay. It's speed it up a little bit. I'm sorry, slow it down a little bit. Right? You can speed it up so fast with this that it almost turns into audio rate and you start hearing a tone. So, the point is you can use this to take any kind of constantly held on gate and break it up at some sort of rate that is equal to this value. And again, the gate itself will be effectively half on and half off for whatever this duration is. So if I set this at, let's see, control click and set this to 400 milliseconds, basically the gate will be on for exactly 200 milliseconds at the current project tempo, and then it'll turn off for 200 milliseconds. So that's that. Let's see now. Latch is a different one. Latch is basically it takes what's coming in, and it's kind of a switch that'll jump between 0 and 1 every time we click some sort of input to this tester here. Okay, now see if you can guess what's happening here. I'm going to click the button on and off. On. I turn it off, but it stays on. I turn it off, but I turn it on again, but now it's off. I turn it on and it's on. I turn it off, it's still on. I turn it on and it's off. What's going on here, right? So this is a tricky one. If you press F1 for the help, you can kind of see better what's going on here. Is whatever comes in here just toggles the output state. So every time something triggers this true, every time this turns solid, it's going to toggle whether this is on or off coming out of it. So it's kind of a weird one. You may or may not find it useful. And you can have other inputs to it that will kind of override this simple toggle behavior. So for example, I could bring another button in here and attach it to the 0, which means false. And now let's say I toggle this so that it's true. But if I toggle this one, now it's false again, because this automatically overrides whatever the current toggle is and makes it a solid 0 coming out of here. Right? And it's just a one-time kind of trigger, right? See, it's still off even though I turned it off. It's like I overrode what the current state was and I just said set it false no matter what. If I bring in another button and hook it up to this one, I can always turn it on. And it's going to stay on because this is just a one-way trigger to always true, but then this will turn it off. And again, it doesn't matter if I turn these off. It's only when they're first toggled and spit out a 1, a true. When a true hits this, it makes this whole thing be 0 or false. When a true signal hits this, it turns this whole thing true and it just stays true until something else changes. So this is a very interesting three-way device where you can always turn it off with a trigger, always turn it on with a trigger, or toggle it on and off with a trigger. And the reason, if I click this and click it again, it turns true, but when I click it off, it stays true. But that's because it only responds to a true signal coming in here. This toggle only flips when this is solid, when something's true hitting us. So this latch device may take a little bit of wrapping your head around, but for some complex sequencing and some sort of randomized sequencing structures that you might build when you get a little more advanced, this can be a very powerful kind of gate device. Now, the last thing we want to talk about are the clock divide and clock quantize. These are very special, and they're anticipating a constant kind of signal coming into them, and that signal usually comes from the LFO section. You see we have something called a clock, And we also have something called a transport. I don't want to jump too far ahead of things and explain these because I am going to have some videos when we get over here, episode 13, 14, and 15. I'm going to be talking about using these transport LFOs, right? So I kind of don't want to get ahead of myself, but the basic idea is these are meant to take an output signal. So we're going to take this yellow signal out from this clock. And the clock is got a rate of 1 hertz right now. And you can see every time it pulses, it's counting up from 1 through 4, and then it resets, well, 1 to 3, and then it resets at 0. So it's 4 steps total that start at 0, 1, 2, 3, and then start again at 0. And every time it hits 0, this turns positive. So this is what a clock divider effectively does. 1 pulse, and then for 2 more pulses of the clock, it doesn't do anything, or 3 more pulses, and then on the 0, it triggers. And on the 0, it triggers. So this is kind of an advanced use case. Some later videos that I do that talk about really, really specific common patterns you might want to do might end up making use of this clock divider, but that's effectively what this does. And then the clock quantizer is a special case that polarity demonstrates really well in that other video I pointed at the beginning of this one, the one by polarity. The basic idea behind this is to, let's turn this off so it doesn't make noise. The basic idea of the quantizer is, you know, if you have a tempo clock from your DAW's tempo, and there's always like a clock running, you know, 1, 2, 3, 4 beats, right? Or a clock that's running at a certain kilohertz rate or hertz rate. If for some reason a trigger signal or a gate signal comes into this one, and it's not on the grid, it's not on the clock, whatever the clock signal is set at, this will make it wait until the next grid value, and then it will let the trigger through. So this is a way of, this is basically for quantizing any kind of incoming clock or trigger signal. It basically will synchronize, like if I turn this on again, 0, and I'm going to hook this up now to the trigger of this. Let's get rid of this one just to really keep it clear. I keep disabling instead of deleting. Okay, so let's say I have a gate. And so I'm manually going to gate notes on and off. Now, here's what's happening. I'm tapping notes, and let's speed this signal up a little bit. Let's slow it down a little bit. Oh, come on, come on, come on, come on, come on. All right. Trying to think off the cuff here. Shush. Okay. Let's see. Polarity did a better job of showing this to you. But the basic idea is if I have some manual signal that I'm doing that isn't on the clock grid, darn it, I'm going to go ahead and just show you with this one because it's a lot easier with this one. All right, let's set this up. And let's slow this down to every half bar. Actually, let's do it every 16th note. 8th note, 8th note, quarter note. Okay. Turn this one on again. Erg. All right. So here's what's happening. Every quarter note, according to my 90 BPM, here's the quarter note pulses coming out of the transport, right? Every quarter note, it triggers a gate. And it's constantly resetting or setting a kind of like logic test saying, has a clock signal happened? Is one of these pulses currently true. Let me see, it'll stay true for a certain short amount of time. Now, if I were to press a key to manually send a gate into here, it's going to say, is that key being pressed or triggered at the same moment that this is true, right? When a new clock signal comes in. And if it's true, then it spits out a signal over here and we actually get the envelope turned on. And then it's going to stay on unless I basically have a note off that happens while this gate is also on. So this is a really weird, you're going to have to wrap your head around this. This is a strange type of logic operator. If I change it to a triggered mode, it'll make maybe a little more sense and be a little less annoying. Okay, so what I'm doing here is I'm tapping my keyboard really fast. I'm going da 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 on the keyboard. But it's only triggering the actual true condition here when my randomly spaced taps on the keyboard are perfectly lined up with this quarter note pulse and this first half of the quarter note that's turned on. If I slow this down a little bit and make this last for a whole half note of every bar, now I'm going to trigger more notes because more of them will happen while this is true, while this port is true. Now I'm constantly going tap, 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 tap. Okay, so this is basically a way to quantize incoming signals that may be irregular to some sort of more regular clock. And that's what this baby's about. So that's pretty much it for these more advanced things. And I'll see you in the next episode. We'll show some specific use cases where now we're doing practical stuff with all this logic testing.